Okay, so this is way more people than I expected. Did you all have coffee? Yeah, because you will need coffee for this talk. Now, first of all, one question. How many of you have a computer science background? Okay, a few of you. And how many of you are self-taught developers or designers or come from other place? Okay, cool. So actually, you know, the intention of this talk is that for people that have that don't have a computer background, this is going to be some kind of introductory crash course from the fundamentals of algorithms. And for people that already had this computer science background, this is just going to be some kind of reminder of all of these concepts. So I know that algorithms and sorting and the word fun aren't normally words that are together in the same sentence, but I'm gonna try my best to make this talk as fun and as interesting for you. So, since this is a JavaScript conference and this is a sorting talk, of course we're gonna be talking about the array sort method in JavaScript. So can you tell what's going on or what's seriously wrong in this example? Can you notice that something is a little bit weird in it? Exactly, it's not sorted properly. So, because normally 25 and 33 comes after the number 4 and not before, right? So what's actually happening? JavaScript is doing this thing called lexicographical sorting. And lexicographical sorting is just the same thing as alphabetical sort or this kind of telephone-like sorting. So, you know, if we don't provide a compare function to the sort method in JavaScript, what JavaScript will do is it will just convert all of the elements in that array into strings. And then it will compare every string according to their Unicode code point value. And this code point value is just the ID of any Unicode character. So in this example, we have a colors array with red and blue. And if we call the sort method, we have blue coming before red because it's an alphabetical sort. But in the case of the numerical array, if we call the sort method, this will be the exact same thing as if we call the sort method with that array and those numbers as strings. And now you might have noticed that 80 has a smaller code point value than 9. So in a more simple way, we can just say that 80 is lexicographically less than 9. Now, in the previous example that I showed you, 25 and 33 are indeed lexicographically less than 4, sorry. So, I mean, it starts to make a little bit more of sense. But I guess that when we're trying to sort a numerical array, lexicographical sorting is not the first thing that pops into your mind. So if we actually provide a compare function to the sort method, we can achieve a numerical sort, which is like most of you have been doing for years, I guess. But here's the big question. Have you ever wondered which algorithm is used behind the native sort method in JavaScript? Because you know, this is just the kind of questions that I love asking myself when I have nothing else to do in a Saturday night, and that's why I don't have a lot of friends, I think. So actually, the answer to this question is that the ECMAScript standard does not really impose a certain algorithm to be used. So basically, this means that the browser vendors can just do and implement whatever algorithm they want. But the good thing here is that most of these JavaScript engines are open on GitHub, or you can just look at the source code and you can actually dig in the code and check the actual algorithm that they're using. And that's exactly what I did. So this is Firefox's SpiderMonkey, and as you can notice, they're using an implementation of merge sort. And what I really like about reading source code is actually reading the comments, because most of them have really, really interesting things to say. And also, I really like reading source code to actually understand what's going on behind under the hood. So this one has a comment that says, the sort is a stable, sequence of equal elements is preserved, and the concept of stability is something that I'm gonna be explaining later. And then there's the second comment that says, apply insertion sort to small chunks to reduce the number of merges. So basically this means that SpiderMonkey is using a combination of the merge sort algorithm and the insertion sort algorithm for smaller arrays to boost performance. Now, Chrome's V8 is using an implementation of quicksort, and just like SpiderMonkey, they're also using insertion sort for smaller arrays. Now, Safari's Nitro is also using an implementation of merge sort, and Microsoft Chakra is using quicksort as well. So now all of this just to sum up that the most used algorithms in these JavaScript engines are merge sort, quick sort, and for smaller arrays is insertion sort. And with all being said, let me introduce you to the beautiful world of sorting algorithms. You know, sorting is the basic building block in which most algorithms are built around. So most of the interesting concepts in the design of algorithms are found in the context of sorting. Things like divide and conquer, like randomized algorithms, and data structures. So actually, by understanding sorting, we can obtain like an amazing amount of power and tools to actually solve our problems in our web applications in a faster or more clever way. And what I'm going to be explaining in the following slides are some fundamentals of computer science. And the first one is the big O, where O stands for order. So how many of you have gone to a job interview and have been asked about the order of a function? Okay, did you know what the big O meant or what time complexity meant? Okay, so how can we know that a piece of code that we just wrote is good enough? How can we measure its efficiency? You know, maybe we can just count the number of seconds it takes to execute, but this is a little bit weird because the same piece of code might not perform the same way in your shiny new Mac computer than in your old Linux computer. So the thing here is that the big O is just a way to measure how well a computer algorithm scales as the data input increases. So let's say how well your algorithm is going to perform when you give it a 10-element array compared to a 10,000 element array. So the big O is just a notation used in computer science to describe the performance or complexity of an algorithm. Now, these are the common orders of growth. And the first one, an order of 1, means that it's constant. It means that no matter the size of your input, the time that it takes to execute will always be the same. Now, an order of n means that the time that your algorithm takes to execute is proportional to the size of your data. And this can be translated into code as a normal for loop. Now, an order of n squared is the same thing as having like a nested double loop, and an order of n cubic is the same thing as having a triple nested loop. Now, the most difficult orders to explain is order log n and order n log n, but I'm going to do my best to try to explain it as easy as possible. So an order of log n is similar to a binary search, in which you have to be eliminating half of the results in every comparison. This means that at the end of the day, you won't be processing the whole array because you're going to be eliminating the other side. And at the end of the day, you're only going to be processing a small chunk of the whole thing. And order n log n is similar to log n in the sense that you also have to keep dividing your array. But in this case, you have to process each array independently, meaning that at the end of the day, you have to process the whole thing anyways. Now, this is a graph that the real takeaway of this graph is that we should avoid having algorithms or functions that are of order n squared and up, because that's like really bad performance. And I really encourage you to do algorithms that are n log n. That's more than acceptable. That's a good algorithm. And now I'm going to be explaining the concept of stability, because I told you I was going to explain that. And basically, a stable sort is just one that preserves the original sort of the input set. And I really like this picture because it makes it very, very clear. So in this case, we have in the top we have a 7 of spades, a 5 of hearts, a 2 of hearts, and a 5 of spades. So basically, the 5 of hearts and the 5 of spades have the same value. Now, in an stable sort, this will mean that the 5 of hearts will preserve its original position, which was before the 5 of spades. In an not stable sort, they won't really matter, and they would put the elements in any position. So now let's talk about the 3 algorithms that I told you are the most used in the JavaScript engines. It's insertion sort, merge sort, and quick sort. And now I'm going to be talking about insertion sort. So insertion sort is an in-place algorithm. And this means that you don't need any extra variable or any extra data structure to actually do the sorting. This is a stable sort, and it's very good for small arrays. Now, the way it actually works is that the insertion sort algorithm will divide your array into 2 different sections. The first section is an sorted section and an unsorted section. Now, in the very beginning of the algorithm, the first element, we can consider that it's in the sorted section. And what will happen then is that the rest of the array is going to be on the unsorted section. And then the algorithm will just be comparing every element to the next one and check which value is smaller than the other. And it will continue checking until the end of the array. Now, I'm seeing your faces, and I know this is not very clear, so I'm going to show you a video to make it work clearer. So in this case, we start with the 6, which is in the sorted section. We compare it against 5. We know that 5 is smaller than 6, so we'll move it before. And we continue checking. We compare 6 with 3. 3 is smaller than 6. It's also smaller than 5. And we move it. And we continue checking. Now with 1, we know that it's smaller than 6. It's smaller than 5. It's smaller than 3. And then the algorithm will just continue checking for the following elements. In this case, 8 is greater than 6, so it keeps its position and it continues. So I guess at this point you have an idea of how this works. Now, this is the actual JavaScript implementation of this algorithm. Now, I don't expect you to read and understand every single line of the code. I'm going to be uploading the slides later so you can actually check them in detail. But what I really want you to take away from this slide is that it has a double loop. And now, if you remember from the previous slide, a double loop can give us the hint that this algorithm has an order of n squared, which isn't that great. And now, the way it's actually working is the first for loop is just looping through all of the elements, and the second for loop is just comparing if the value is smaller or greater than the other. Now, this algorithm has a performance of n squared, and then n squared in its worst, in its average case, and in its best case, it has an order of n, which means in the case, for example, if we give it an array that it's already sorted, the algorithm will never go through the second loop because it will only go through the already sorted section. And now let's talk about merge sort. I really like merge sort because it introduces a really nice concept of computer science, which is the concept of divide and conquer. Now, divide and conquer has this philosophy behind that it's way easier to solve a smaller problem than a bigger problem, of course. So what it actually do is keep dividing your problem into small pieces until you can actually just solve the small piece. Now, the way the merge sort works is that it will divide the array into 2 subarrays recursively until you have a 1-element array. Now, a 1-element array is already sorted, right? Because 1 element, there's nothing against to compare, so that's already sorted. And now that you have these 1-element arrays, you can all just merge them back together to have your already sorted array. Now, then again, this is way easier to explain with a video. So we start with our array, we divide it into halves, and we keep dividing these halves into halves, and then into halves until we have 1-element arrays. And now we're going to apply, or we're going to merge back together these 1-element arrays. So in this case, we have 1 coming before 3, 7 coming before 8, 2 and 4 are already in the right position, and we continue merging back these arrays. So the actual implementation in JavaScript is it's very easy. In this case, we have a middle variable, and what it's doing is just taking the middle element of the array, and then it's just this left variable is just slicing the array from 0 to the middle part of the array, and the right part is just slicing the array from the middle to the end. Then this last line of code is just calling the merge sort function in the left array and in the right side of the array recursively, and then it's just merging back together the whole result. Now, the most interesting part of this implementation is not the merge sort function itself, but the merge function. Now, the merge function receives 2 already sorted arrays, and then we have a results array, and it will check from both arrays which value is smaller than the other. And once it has a smaller value, it will push it to the result array. And at the end of the day, when we finish checking all of the checking one array or the other, the rest of the elements are just gonna be concatenated to the end of the results array. Because if you remember, these 2 arrays are already sorted. So The performance of this algorithm is n log n in all cases, which makes it a very good and performant algorithm. Now, the next one is quicksort. And quicksort is similar to merge sort in the sense that the sort is accomplished by dividing the array into partitions. And then those partitions are resolved recursively as well. Now, the way that quicksort actually works is that we have to choose a pivot element, and it can be chosen in very different ways. In this example and in this implementation, it's going to be by choosing the middle element of the array. And what we have to do is we have to put all of the elements smaller than the pivot to the left, and all of the elements bigger than the pivot to the right. It doesn't really matter their order as long as they are either to the left or either to the right, depending if it's smaller or greater. Now, the way this actual implementation works with JavaScript is, sorry. Yeah, so in this case, we have 3 as the pivot element, and we have 2 pointers. One pointer to the beginning of the array, and another pointer to the end of the array. And the way that it works is that we're going to be moving these pointers in the array until we find a value that is not on the right side. So in this case, 5 is not on the right side because it's bigger. 8 is fine. 1 should not be there. And once we find these values, we swap them. And in this case, you can notice that 1 and 2 are smaller than 3, and the rest of the array is greater than 3. So in this case, we're left with 2 arrays, an array of 2 and 1, and an array of 5, 8, 7, 6, and 4. And what we will do next is just call the quicksort function recursively in those arrays. Now, the implementation. So here, the very most important part is the partition function, which is the one in charge of actually finding the pivot and moving the elements to either one side or the other. Now, if you can notice here, after calling this partition function, we just call recursively the quicksort function in either the left side array or the right side array. And then again, the most interesting part is actually the partition function, not the quicksort function. So what this is actually doing is in the very top, we're finding the middle element of the array. Then we establish it as the pivot. Now the I and j variables is the left and right pointers. And then we have 2 while loops, and the while loops are just moving the pointers away. And this last part is just making the actual swapping. And in this case, I'm using ES6 destructoring swap. Now, this has a performance of n squared, and in its worst case, and its in average case, it has an n log n performance, which also makes it a very good algorithm. Now, you can even extend array prototype with these algorithms, and you can use it as if they were native. So that's pretty cool. Now, if you're still awake and if you're still with me, congratulations, you just survived the most computer sciencey part of the talk, so good for you. Now, why should you care about all of these things that I just told you about? First of all, design strategies. We just talked about concepts like big O notation, like divide and conquer, recursion, in-place algorithms. You know, knowing all these things can give you a really great amount of power to actually solve your problems in a different way. It changes the way you think. It's a different mindset. We have to design our functions in terms of complexity to boost performance. Now, then again, these concepts are not exclusive to the world of algorithms. We can use it anywhere. And this is a tweet by Dan Abramov in which he was saying that he used the divide and conquer technique to actually debug his CSS code. Basically, what he did is that he had something going on that was not working, and then he was just commenting half of his CSS code and commenting half and half and half until he finally found his bug. Now, talking about sorting itself, why would you ever care about writing your own sorting algorithm when there is already a JavaScript one? And the first reason is because of stability. So if you care about having a stable sort, let me tell you something. The native sort method is not necessarily stable, and I'm quoting the MDN docs. And the second most important reason is because of performance. Now, JavaScript sorting algorithms can be definitely faster than the native one, by a bunch of reasons. It can either be the amount of space that you have, the kind and quantity of data that you're going to be sorting, and also the JavaScript engine that you're going to be using. Now, as you notice, creating your own sorting algorithms in JavaScript is not that difficult. I just did it in a few lines of code. But this is a huge warning. I'm not saying that you should just go back home and like re-implement everything. It's not the case. We have to learn how to pick our battles. Now, if you were not sleeping during the talk, you might have noticed that V8 and Nitro, it's actually, the implementations of these algorithms are actually in JavaScript itself. So this is some kind of like JavaScript inception, because the JavaScript engine is written in JavaScript itself. But it's so weird. But actually, there is a computer term for that, and that's called self-hosting, which is implementing parts of a language in that very language itself. And maybe at this point you're like, yeah, but why would we implement that in JavaScript? That's slow. So actually, no. Array methods cannot take callbacks as an argument. So they iterate over that list, and for every element in the array, they will call this callback. Now, the execution has to switch between compiled C++ code and also interpreted JavaScript. So this context switch is expensive. So if we actually stay in the same execution context and in the same language, we can actually boost performance. Now, SpiderMonkey and Chakra are not self-hosted, and V8 and Nitro are. And now, just before I end, let's do some benchmarking. So I actually tested the native sort method and the implementations of the 3 algorithms that I show you, and this is what I got. So I tested it with the randomly generated elements. So with 10 elements, insertion sort is actually faster than the native sort JavaScript method. With 100 elements, insertion sort is still faster. With 1,000 elements, insertion sort, surprisingly, is still faster than the native version. With 100,000 elements, insertion sort is no longer faster, but quicksort is faster than the native one. And what will happen with a 1 million element array? So first of all, my computer froze with insertion sort, yeah. So for the following examples, I'm not going to be showing insertion sort. So for a million element, quicksort is still faster than the native version. And just for the fun, the last one, with 10 million element array, quicksort is still faster than the native version. So here is your homework, because this was like a crash course, right? So play around with all of these things, testing different machines, test with different input sizes, with different JavaScript engines, because you know, these tests were done in my Mac computer, in my Chrome browser, and of course results are gonna vary if you test in different computers or in different browsers. So that's your homework, like play around with this thing. And with that being said, congratulations, you have all finished Claudia's sorting algorithm certification. Now you are all sorting algorithm experts. And now is your time to actually implement your own versions of these algorithms and check what is best for your project, what works best for your applications, and try to have some fun. And the craziest thing about it is that computer science people or computer science students actually study this thing at school, and after that they have no idea how to put it into real life, how to actually use it. And then there is self-taught developers that at some point they just are thinking how to create these things, but everything is already available online. There's a lot of people that have already thought and studied a lot about these algorithms. So we actually have to learn how to take profit of all of these really, really intelligent people that already did that thinking for us. So with that being said, I really, really hope you like this talk. Grazie mille. My name is Claudia Hernandez, and thank you.